Thank you for coming to our poster presentation. We are students in a graduate seminar course on managed aquifer recharge at the University of Memphis. Our study aims to identify ideal locations for the implementation of infiltration galleries in eastern Arkansas. For a little bit of background, the Mississippi River alluvial aquifer, or MRVA, is a primary source of agricultural waters in the region, but a confining clay layer near ground surface limits recharge. As shown in Figure 1, large-scale cones of depression have formed west of Crawley's Ridge, which has led to the state designation of critical groundwater areas. Our focus is specifically the Cache River Critical Groundwater Area. Infiltration galleries are shallow, gravel-filled trenches constructed in the unsaturated MRVA sediments. Nearby on-farm storage reservoirs serve as the recharge source water that would flow through the gravel fill through the unsaturated MRVA sands and gravels before reaching the water table as shown in Figure 2. The main goal of infiltration galleries are to increase the groundwater supplies, which become viable conservation practices for producers throughout the region. One reason we are presenting this in Tennessee is that infiltration galleries could prevent producers from needing to pump water from the deeper Memphis-Sparta aquifer, which is a primary water source for West Tennessee.
So in order to select these infiltration gallery sites shown on Figure 5, we used ArcMap's GIS utilizing different sets from the USGS Airborne Electromagnetic Flyover Survey. And using the query tool, we prioritized a thin confining unit of less than 4 meters for ease of construction, a low vertically integrated conductance of less than 0.2 for materials with high permeability, and locations within 60 meters of on-farm storage reservoirs. So Figure 3 shows the flight lines loaded onto GIS with the selected query output shown in blue. And then if you look at Figure 4, that gives a visual representation of the subsurface through resistivity, VIC, so vertically integrated conductance, and clay thickness. After we queried for the previously mentioned features, we checked if the sites had depths to waters of over 25 meters, and we did this by interpolating discrete depth to water well measurements into groundwater surface layer in GIS using the natural neighbor method.
Out of these, there were 9 out of the 143 sites near the Cache and Lingill River that could be chosen with the site with the parameters. Our hypothesis is that the river had eroded some of the confining unit. From those 9 sites, we picked 4 with the depth to groundwater greater than 25 meters, low vertically integrated conductance, and a thin confining unit. The idea is that these sites do not take land out of production for farmers and consumers, and that sites that were near rivers and ditches were relocated to a better location. In Figure 6, Site 1, it is the first site that we picked in Poinsett County, Arkansas, which is in a forest. This has less than 1 meter of clay thickness, below 0.20 VIC, and the depth of groundwater is about 32 meters. In Figure 7, Site 2, is a gallery in Cross County, Arkansas, and also in a forest. This site had the best parameters, meaning that there was less than 1 meter of clay thickness, below 0.20 VIC, and the depth of groundwater was about 26 meters.
Site 3 is in Poinsett, Arkansas, and has the greatest depth to groundwater out of all the sites at 37.1 meters. This site is represented in Figure 8, and our infiltration gallery would be placed west of the reservoir in a wooded area off an access road where construction and excavation can be more easily accessible. Site 4 is in Poinsett County, Arkansas as well, and has a depth to groundwater at 34.6 meters. This site, which is represented by Figure 9, has the largest reservoir, and the infiltration gallery would be placed just north of the access road that runs the perimeter of the reservoir. This land is also wooded and is out of production like in Site 3. So producer collaboration and land access will be key in the future of this project. Contact and land agreement with farmers and businesses will be necessary to further investigation. The next steps would then be to use ground-based geophysical surveys to affirm our AEM survey data, and site-specified coring and samples would help validate the subsurface materials. Lastly, reservoir quality would also need to be established, and additional site-specific investigations would determine the validity of these determined sites. We would like to finally acknowledge the AEM data and subsurface map from Stephanie Jones, Burke Minsley, and J.R. Rigby with the USGS Mississippi Alluvial Plain MAP project. And thank you for listening to our presentation.